So as an architectural office who is heavily investing also in research, it's a nice challenge to participate in this kind of research project. And it's even more interesting and challenging if at the same time we were designing our own new office building, where of course then also as an architecture office, you want to push the limits. So the design of this office actually went a bit similar or the same timeline as the research project. But resilience as such in the beginning was not our main concern. Of course, it was something that we had in mind, but we wanted to design an office building which also had actually a very low cooling demand. Actually, we wanted to have no heating demand nor cooling demand, but given the Belgian context, that's a bit challenging. And also given the fact that our new office building will not be built in a greenfield. Actually, we will move in next month if everything goes well. But it's actually an inner city development near the railway station of the city of Leuven, the biggest university city of Belgium. So it has all that complexity in it that the current urban developments in them have. So, but we wanted to challenge this project, and I think most of you know that current office buildings have even a cooling demand which is higher than the heating demand. They also have a considerable ventilation demand. So we thought it was already a very nice accomplishment if we could design an office building which would have no cooling demand in the current Belgian climate, but we also were interested in the future climate, how it would behave. And that's why we jumped into literature. And one of the studies that we found was of Delphine Ramon, now a graduate PhD student from the University of Leuven, who actually has had in a PhD identified the big parameters which influence the cooling demand of the current climate, but also on the future climate. At the same time, there's also the PhD of Anis Machar, who did a bit the same things. And so orientation was one of the aspects which was identified. Window to wall ratio, as also was already explained by Douai. Also, as Douai has said, that we took quite some inspiration on the design for reducing overheating to identify also the parameters who could have an influence on the resilience. Shading, of course. And one aspect which was not included in the study of Delphine Ramon was the one of ventilative cooling, but that was in the study of Anis Machar, and she showed also that combining thermal mass with ventilative cooling had a very good high impact in the cooling demand of our buildings. So we took this parameter to design with, and the challenge then of the resilience research was to see if we have done a good job. And people who had a quick look at the graphs which were shown by Dua will have seen that indeed the job we have done seemed to have also a very good result when it comes to resilience. That's why I now will present our design process as a kind of designer's guideline, how a building could be designed to have a good resilience to overheating. But of course, I will make quite some connections to the summer comfort and to the overheating. So as said, the main parameters which we will research are the ones on the window to wall ratio, on the shading, on the ventilative cooling, and thermal mass. And let's start with the first two of them. And maybe it might be a surprise to you, to the people who now are participating, who are not designers, but for a lot of architects, still defining the right window to wall ratio is a challenge, and also getting a grip on the shading strategy. Well, then most of the time we're showing this kind of graphs, which come from the European Passive Solar Handbook, which is already a quite old publication, which say that actually a mean window to wall ratio of 40%, and it was also in the range which was tested in the resilience research, is actually a good point, a good starting point. But which is also said in the publication, it makes sense, of course, that it's not very logical to have the same window to wall ratio on each orientation, although we still see quite a lot of buildings designed in such a way. But as the sun is, of course, interacting differently on each orientation, it's important to vary the window to wall ratio according to the orientation. The European Passive Solar Handbook is providing this guideline, the graph you see on the right, although we're thinking that in the publication one point is maybe a bit missed, and that's a fact that, as shown here also in these graphs of the Birkhauser Energy Manual that on a summer's day, actually, the solar load on east and west facade is higher than the one on the south facade. On the winter, it's inverse. In the winter, indeed, on south, you have the highest solar loads. So we always adapt this graph in such a way that we say, okay, on south, you can have a bit more glazing ratio. You also then take the profit of the solar gains in winter. On east and west, you need to very well keep the ratios in mind. Okay, but that's of course easy if you have the clear orientations, having a building in a green field. That's of course never the case, or not a lot of case anymore. Luckily enough, we're not building a lot anymore in green fields. So how then can you address this challenge? Well, this is an example of a hospital building. It's not of our office building, but I think this is clear. Well, actually, we're doing annual and solar radiation studies, annual and also during the overheating season, so during cooling season on the facade. And there actually we help them to correlate window to wall ratios actually with the result you see very graphically on the simulations. And what this kind of simulations can learn us? Well, in first instance, it influences actually how you're programming your building. You can identify the highly exposed facades. Well, we know that certain spaces, due to their size, due to their activity, are quite sensitive to overheating. So these will try to put away, of course, from these highly exposed facades. Of course, as already said, influence on the position on the windows and the sizing of the windows. It helps you to identify exposed parts of the facade with the same characteristics, so you can apply the same strategy on your facade. And it also helps you to anticipate and also test passive solar protection strategies. So actually with this quite simple tools, the simple ratios, the simple simulations on the facades that you can even do with free plugins on SketchUp, but also on more advanced simulation software, you already can do quite a lot in preparing your design for having a high resilience. Then the next step is the ventilative cooling and thermal mass, and that's indeed already a bit more complicated. Just to show how ventilative cooling is implemented in our new office building, well, we work with natural ventilative cooling because we need quite a high air change ratio to cool down our thermal mass. And of course, we want to avoid that we have mechanical ventilation running all the time and consuming, which is of course against the concept that we have in mind. So during nighttime, when the conditions are favorable, we have the natural ventilative cooling. It can happen under certain conditions in Belgium that you have temperature inversion, that you don't have the chimney effect, the stack effect. And so then our air handling unit the extraction can help to raise the ventilation, the air change rates in our building. But another aspect that, of course, now that we have invested in all these means of letting controlled air natural ventilated through our office building, it would be a pity not to use that also during daytime when conditions are favorable. I already mentioned that ventilation is also one of the big consumers in our nowadays office buildings. So whenever it's possible, we also use these operable windows, this control system to provide our natural hygienic ventilation. Okay, but then how do you start on this? Quantifying and assessing of this natural ventilation will work. How should it work? Well, there we used a 3-step procedure, and we built upon a tool which has been developed during the NX62 research project, the ventilative cooling tool, which is actually freely available on the website of this NX project. And it allows you through some simple input in Excel to assess what's the potential of your building, size, or location, orientation, programmation, to take profit actually of natural ventilative cooling. So it's a quite easy assessment, quite low level, of course quite rude, but you don't need to have details at this moment. As a second step, when you're convinced that it's indeed a feasible concept, we just did a single zone dynamic simulation. There are quite some low-level tools available for that, which allow you to check the ventilation rate that you can have just by assessing the stack effect. So taking no wind effects into account, which brings you mostly at the safe side, and assessing indeed already how it might impact your cooling loads. And as a last step, we then put a step to a full multi-zone dynamic simulation, for which we also used the simulation results to test the resilience indicator. And I will not go into depth in this, but so the building has been modeled in either eyes. Controls have been made for the operable parts. And this also results in a visualization. And I like to emphasize also the importance of this kind of visualizations, because it helps for sure as a modeler to check if the building behaves as you expect, but also to convince actually all the partners in the design team, and of course also the client, of this kind of concepts. In this project, we are investing ourselves in the project, but even then there was a lot of conviction necessary. And if you then can show how actually the stack effect, stratification effect will work in the building, if you can show how this kind of natural ventilation can work, it can help. In our project, we have still have added mechanical cooling, because future climate simulations has shown that on the long term we would need mechanical cooling, also to have this kind of plan B. Of course, because we have this natural ventilative cooling, we didn't want to have the issues, the burden of a risk for condensation on radiant cooling systems. So therefore, we applied a system in which we have integrated the cooling, the potential cooling or heating tubes in a clay system, which actually does not mind that there is condensation because it absorbs this. So in this way, we can really make a real hybrid cooling concept where there are no risks which are classical connected to this kind of technologies. And which is very nice if you then look towards the energy balance graphs. The one that you're seeing now are for the scenario of only mechanical cooling, so what we're not having, but we wanted to see what the impact is. The first graph is a week beginning of July, where you already have quite some cooling demand. You see that through the light blue elements each day during daytime at the negative side, so there is an extraction of energy. And you see on the right, even the hottest week we have in our model, the first week of August. If we then look what happens if we have this kind of hybrid cooling concept, natural ventilative cooling with mechanical cooling, you see in the purple parts, where actually this ventilative cooling is extracting energy out of the building. And you also see that, and that's on the dark brown parts, how the thermal mass really is activated, loading and unloading the whole time. At the right, you see during this very hot period, when it's too hot actually to have the windows open, then mechanical cooling kicks in. But of course, you see it's quite less. So to assess the impact and the effectivity of what we have been designing, we've made several scenarios: only mechanical cooling, adding shading, adding mechanical ventilative cooling, going to high thermal mass, adding natural ventilative cooling, and also natural cooling through the TAPS system. I will not show all the results, but the graph to the left I think is interesting because it shows us the energy use for cooling in 3 zones. In the 6 scenarios, from which actually scenario 5 is the one which we are having constructed now. The orange graphs show on the current climate what the cooling demand is. You see that in scenario 5 it all reduces to 0. In gray, you see what on the long-term future climate, and that's in 2070, 2100 in the RCP 8.5, so actually the worst case scenario, what the cooling load will be. And it was very important for us also to show and to learn that even on the future climate, these kind of strategies really make sense and they help in reducing the cooling load. How much do they help? Well, this is shown in this graph, which is actually taking out the two most extreme scenarios. So we see that through the adding of the natural ventilative cooling under current climate, we reduce the cooling demand by 80%. So it actually virtually nothing. Under future climate, so the RCP 8.5 as said, we still are reducing it by 60%. So we will have a cooling demand by that period. If we look in absolute figures, we see that nowadays we gain 15 kWh per square meter, but in the future climate, we will even gain more. In this case, 18 kWh per square meter. Why? Well, of course, the cooling demand is larger, but also the cooling periods will be longer. So the period also in which we have favorable conditions for validating this ventilative cooling concept. And this graph has already been shown by Duai. So if we then do the assessment towards resilience, the strategies are a bit different. So the A is the no strategies, the B is dynamic shading, F shading and cooling, G shading, natural ventilative cooling, and then H cooling, shading, and natural ventilative cooling. You see that actually only in the A, even in the A scenario, our design of our buildings is already so good that it stays resilient class 2. And then by adding the other scenarios, so the regression model predicted some set degree hours, but the simulation showed actually that there are no set degree hours anymore. So it proves through this resilience test that the design that we have made through these kind of strategies, through the steps that we have followed, has resulted in a high resilient building. And then a short on the cost, because of course, what's the investment cost, the operational cost, and the investment cost? Deborah Resta will dive even deeper in this, but just to show what's the energy amount on yearly base on the cost in kilowatt hours per year. So in the A scenario where there is no strategy, of course, we have of course no cooling demand because there's no cooling. We have heating demand and we have fan power. We see in B, when you have actually cooling, you see that there is a high cooling demand. So the two blues are for the two different heat wave scenarios that you have there. Each time midterm for the city of Ghent, most intense and most severe. You see that you add shading, of course, your cooling demand decreases. When you go to the G scenario, the shading and natural ventilative cooling, of course, you don't have any mechanical cooling anymore, so your mechanical cooling demand goes to 0. But if you get into the H scenario, what we actually are building, you see that we still have made a huge gain in cooling demand operational through this scenario. If you then look to the additional upfront investment cost, well, there, of course, no surprise. Case A is costing us nothing. Case B is cooling. We invest in the cooling system, distribution system, production system. If you add the cost for the shading, G, well, you don't have any cooling system anymore, so you only pay for the shading and the additional cost for the natural ventilative cooling. So that's the automatization of the windows and the controls. And then case H indeed is the most expensive because you're adding up the costs. But if we then look towards the total cost over 20 years, the yearly cost, we see that actually case H is the best case cost-wise, which actually guarantees comfort because case A and case G don't have any mechanical cooling. So to be short, how to build future-proof, study the orientation and solar exposure, restrict the window-to-wall ratio depending on the solar exposure, provide shading, no surprise, provide preferably natural ventilative cooling, use the thermal mass, and most buildings already have invested in it, so it's there, so please validate it, and use common sense. And I added as a gimmick, but not as a gimmick, fans, because that's also one of the means that we are applying in our new office building, a completely forgotten technique in the middle and the north of Europe, but very effective. Just by having a higher air velocity, you have much better summer comfort. This case study is also published in the latest RIVA guide on resilient cooling's design guidelines. So people who want to consult this are always free to do it. And now I'm happy to give the word to Deborah for explaining us the case studies that Arcadis has done.